Okay, so we're dealing with gene expression data. We have measurements for 100 different genes, and these measurements are from 200 different patients. This is our first dataset, X. Okay, so we're dealing with gene expression data. We have measurements for 100 different genes, and these measurements are from 200 different patients. This is our first dataset, X. This is our second dataset, Y. It contains 5 different clinical measurements, also taken from the same 200 patients. We'll be comparing these clinical measurements to the gene expression data. This is our second dataset, Y. It contains 5 different clinical measurements, also taken from the same 200 patients. We'll be comparing these clinical measurements to the gene expression data. We're using canonical correlation analysis, CCA, a statistical method to find relationships between datasets X and Y. The (n_components equals 2 part means we're looking for two major relationships or patterns. Think of it like trying to find two major ways the gene expressions relate to the clinical measurements. We're using canonical correlation analysis, CCA, a statistical method to find relationships between datasets X and Y. The (n_components equals 2 part means we're looking for two major relationships or patterns. Think of it like trying to find two major ways the gene expressions relate to the clinical measurements. (X_loadings_) is the output of the CCA model. It shows us the relationship between each of the 100 genes, rows, and the two major patterns or relationships, columns, found between X and Y. Think of it as how much each gene contributes to defining those relationships. (X_loadings_) is the output of the CCA model. It shows us the relationship between each of the 100 genes, rows, and the two major patterns or relationships, columns, found between X and Y. Think of it as how much each gene contributes to defining those relationships. Similarly, (Y_loadings_) tells us the relationship between the 5 clinical variables, rows, and the same two major relationships or patterns, columns. It shows how much each clinical variable contributes to describing those relationships discovered between the two datasets. Similarly, (Y_loadings_) tells us the relationship between the 5 clinical variables, rows, and the same two major relationships or patterns, columns. It shows how much each clinical variable contributes to describing those relationships discovered between the two datasets. This statement is true. Remember, canonical variates are new variables created as combinations of the original genes. The (X_loadings_) give us the weights showing how much each original gene contributes to each of these new canonical variates. Stronger weights mean a stronger correlation. The dimensions are correct, but the interpretation isn't quite right. The (Y_loadings_) show the weights, not the correlation directly. Think of it like this. The weights show how much each clinical variable contributes to each canonical variate. The correlation is implied but not directly the value of the weight itself. This is true. The (X_loadings_) are essentially the formulas for calculating the new canonical variates from the original gene expression data. Each column represents a separate canonical variate, and the entries within each column show how much each gene contributes to that particular variate. This statement is false. The magnitude of a loading only tells us relative importance within a canonical variate. A large value in one variate might be less significant overall than a smaller value in another variate that has a much stronger correlation between the datasets. It's all relative. Hey Vamsi, this line introduces the core problem. We're using a statistical technique called canonical correlation analysis, CCA, to find relationships between gene expression data and clinical measurements. Think of it as looking for patterns that link genes to patient health outcomes. This is one of our datasets. It contains information on gene expression levels. Each row represents a different patient, and each column represents the expression level of a specific gene. So, dataset X has measurements for 100 different genes and data for 200 different patients. This is the other dataset. It shows various clinical measurements for each patient. These could include things like blood pressure, weight, etc. Dataset Y has 5 different clinical measurements recorded for each of the 200 patients. We're using CCA with n_components equals 2. This means we're looking for two main relationships between the gene expression and clinical measurements. We're simplifying the complex relationship between the two datasets into just two main aspects. This is where we run the CCA analysis. The model finds the two most significant relationships between the two datasets. This is an output from the CCA model. It tells us about the relationship between each gene and the two main components, or relationships, it found. We want to understand what each gene's contribution is to those relationships. The output x_loadings_backquote is a 100 by 2 matrix. There are 100 rows, one for each gene, and 2 columns, one for each of the two main relationships found by CCA. Similarly, this output tells us how each clinical variable contributes to the two main relationships found between the datasets. The output y_loadings_backquote is a 5 by 2 matrix. 5 rows, one for each clinical variable, and 2 columns, one for each relationship identified. This refers to interpreting the numbers in x_loadings_backquote and y_loadings_backquote. These numbers represent how much each gene or clinical variable contributes to each of the two major relationships. The numbers aren't correlations themselves, but rather weights which indicate the strength of the relationship. A higher absolute weight implies a stronger relationship for a specific gene, clinical measurement, and CCA component. This is a multiple-choice question, testing understanding of canonical correlation analysis, CCA, and its output in the scikit-learn library. The question focuses on interpreting the x_loadings_backquote and y_loadings_backquote attributes after fitting a CCA model. It's designed to assess whether you understand how these attributes relate to the original data and the canonical variates generated by CCA. Let's dive into the specifics of the question. This question asks to evaluate the correctness of 4 statements concerning the interpretation of x_loadings_backquote and y_loadings_backquote from a CCA model. The statements explore what the values in these attributes represent and how they can be used to gain insights about the relationships between variables in the two datasets. This is where your understanding of CCA will be critical. Think about what CCA does and what its outputs mean to effectively tackle this. Statement A claims that x_loadings_backquote displays the correlation between each gene in dataset X and the first two canonical variates, principal components, of that dataset. Remember, canonical variates are linear combinations of the original variables designed to maximize the correlation between datasets X and Y. Therefore, A is about understanding if the loadings themselves show the correlation directly. Statement B states that y_loadings_backquote has dimensions 5, 2, indicating the correlation between the 5 clinical variables and the 2 canonical variates of dataset Y. This checks your understanding of the dimensionality of the output and its connection to the input data size and the number of canonical components. It also tests if you understand whether these values are correlations or something else. Statement C asserts that the columns of x_loadings_backquote are the weight vectors that project the data in X onto its canonical variates. This probes your understanding of how the loadings are actually used in the CCA process. Think about the mathematical process. Do the columns represent weights used to map the original data into the new reduced dimension space? Statement D suggests the magnitude of the elements in x_loadings_backquote and y_loadings_backquote directly reflects the feature importance. This statement explores whether the absolute size of a loading alone sufficiently conveys the importance of the associated feature. Consider the relative importance of loadings within a canonical variate, not just their individual magnitudes. Which of the following statements are true regarding the interpretation of these attributes? XLOADINGS and YLOADINGS. This question assesses your understanding of canonical correlation analysis, CCA, results from the scikit-learn library. We'll explore the meaning of the XLOADINGS and YLOADINGS attributes in the context of a CCA model fitted to gene expression and clinical data. Let's explore option A. It claims that the XLOADINGs show the correlation between each gene and the first two canonical variates, the new combined variables created by CCA. This is a key concept of CCA. How much each original variable, a gene, in this case, contributes to the new, combined variables. We'll revisit this to see if it's a true statement. Option B focuses on the dimensions and interpretation of YLOADINGs. It correctly states the dimensions, 5 clinical variables x 2 canonical variates. But, it needs to be clarified if the interpretation as correlation is fully accurate. We need to be careful here about what the numbers represent. Are they direct correlations, or something else? This will help us determine the validity of this statement. Option C describes the columns of XLOADINGs as weight vectors for projecting the original gene expression data, X, onto the canonical variates. This is a core concept of CCA. The XLOADINGs give the weights for each gene to create the canonical variates. Let's check if this is consistent with the other information in CCA principles. Option D suggests that the size of the numbers in XLOADINGs and YLOADINGs directly indicates feature importance. This needs careful consideration. While magnitude provides some indication, it's crucial to understand that the relative importance depends on the context, which canonical variate we're looking at, the overall correlations, and other related information. We must think critically about how to interpret the magnitude in this scenario. This section sets the stage. It gives us the context by defining the two datasets used. X, gene expression data, with 200 samples and 100 genes, and Y, clinical measurements, with 200 samples and 5 variables. This data is what canonical correlation analysis, CCA, is applied to. Dataset X is 200 samples across 100 genes. Each sample is a patient, each column is a gene, and each cell represents the expression level of that gene for that patient. Dataset Y represents 200 samples across 5 clinical variables. Again, each sample represents a patient, each column represents a different clinical measurement, and the cells show the clinical values for each patient and measurement. The CCA model is applied with n_components equals 2. This means CCA is creating two new variables, canonical variates, that capture the maximum correlation between the gene expression and clinical data. These new variables are linear combinations of the original variables. The XLOADINGs matrix has dimensions 100 rows, for 100 genes, and 2 columns, for the 2 canonical variates. Each element represents a weight, showing the contribution of a gene to a specific canonical variate. The YLOADINGs matrix has 5 rows, for 5 clinical variables, and 2 columns, for 2 canonical variates. Similar to XLOADINGs, each element is a weight, reflecting the contribution of a clinical variable to a specific canonical variate. This quiz problem explores understanding canonical correlation analysis, CCA, using the scikit-learn library in Python. The goal is to interpret the meaning and significance of the *x_loadings_ and *y_loadings_ attributes output by the CCA model, specifically focusing on how they relate to the original datasets and the canonical variates. It presents a scenario involving gene expression data and clinical measurements, and asks you to determine which statements correctly interpret the CCA results. This requires understanding the core concepts of CCA, canonical variates, loadings, and correlations. Let's break it down. This statement assesses understanding of *x_loadings_. The question is whether the values in *x_loadings_ represent the correlation between each gene and the 2 newly created variables, canonical variates. Think of it like this. CCA finds new variables that maximize correlation between the datasets. *x_loadings_ shows how much each original gene contributes to creating each of these new variables. Is that making sense? This statement tests understanding of *y_loadings_ dimensions and interpretation. The dimensions, 5, 2 are correct. 5 clinical variables and 2 canonical variates. However, it incorrectly says that the values directly represent correlation. Instead, they represent the weights used to form the canonical variates from the clinical measurements. It's a subtle but important difference. This statement examines understanding of how loadings are used in the projection step of CCA. It's asking whether the columns of x loadings are the weight vectors used to transform the original gene expression data into the new canonical variates. Each column represents a different canonical variate, and the values within the column are the weights applied to each gene to project it onto that variate. Let's think about this together. This statement explores the interpretation of the magnitude of the loadings. It suggests that a large value directly implies high importance. However, the importance of a feature is relative. While magnitude indicates contribution to a specific canonical variate, it doesn't give the overall importance of the feature across all canonical variates. Think of it like this. A large value in one variate might be less important than a small value in a highly correlated variate.